right, let's get started. So, again, if you haven't watched the first yet, do that. Watch the first video. Don't watch this video yet, but I'll provide links to that. We're going to talk about line integrals over vector fields. We're going to review that right now. This is a part of the first video, so we're only going to do four of these problems about line integrals over vector fields. So problem 1 says, evaluate f dot dr for the vector field q cosine y 3xz z e to the y over the curve c parameterized by that from the points blah blah blah. Use these 4 steps. For this one, you use the 4 steps. God, it's so bright. How's that look? Does everyone see that just fine? It looks pretty good on my. Is everyone good for that? Is that good? Any problems? Okay. Words. Okay. Our vector field is 2 cosine y, but instead of saying 2 cosine y, we're going to plug in what the parameterization was given to us to be. We were told that y was equal to t squared, right? 2 cosine t squared. Hope this works. Comma. I'm writing a lot slower here. 3xz. Well, x was 3t squared plus 1. So we have 3t squared, 3 times 3t squared plus 1. I feel like, ugh, not that pretty. Times z, and z was equal to 2t. And then we have z e to the y. Well, z is equal to 2t, and e to the y would be e to the t squared. Is everyone good on my vector field? I've plugged into my vector field, right? Now, what do I dot this with? I dot this with r prime. So I'm going to say dot. Cool, it's on screen. I'm going to dot this with r prime. Well, r prime would just be the derivatives of 3t squared plus 1, 2t squared, and 2t. So 6t, comma, 2t, comma, 2. So step 1 was find your parameterization. The nice thing about step 1 is that was already done for us. We didn't have to find a parameterization. The parameterization was already given to us. Step 2 was compute r prime. We did that and we put it here. And then step 3 was kind of plug everything. I kind of did that beforehand, but so we have our setup. We're going to dot this out. We're going to get, when we do this dot product, we get 6t cos. Great. Where's undo? Where are you? I thought there was a. Oh, way up here. Cool. Make fun of my head. Oh, and then I brush. This is going to be a nightmare. All right. 12 cosine of. Well, was it 12t? 12t cosine of t squared plus. Oh, what a mess here. With 3 times 3t squared times 2t times 2t. So that would be 36t cubed. T to the 4th. 36t to the 4th. Plus 3 times 2 times 2 will be 12t squared. Plus, and then we dot the 2t e to the t squared times 2, so we get 4t e to the t squared dt. And we're going to evaluate this from where to where. What are our bounds on t? Oh, they don't give them explicitly to us. They don't explicitly tell us our bounds on t. So that makes things a little difficult. We are told we're moving from the points 1, 0, 0 to 4, 1, 2. So what we're going to do is set our parameterization, 3t squared plus 1, comma t squared, comma 2t, and set those equal to the first coordinate and the second coordinate. If we set 3t squared plus 1, comma t squared, comma 2t equal to 1, 0, 0, what value of t does that correspond to? That is to say, we have 1, 0, 0. And we're setting it equal to 3t squared plus 1, comma, t squared, comma, 2t. Right? For what value of t is that true? Yeah. 0. So that's our lower bound of this integral. For what value of t is this guy equal to 4t squared, or equal to, sorry, for what value of t is this equal to 4, comma, 1, comma, 2? Equal to, for 1, t equals 1, right? So our upper bound is 1. So then it's a matter of doing the integration. This integration is not so bad. It just requires a couple of u subs. You would do a u sub here for u equals t squared, and you would get 6 sine t squared. That looks like a theta. Just because I'm writing so poorly on this board, I thought I would look a little more like Minority Report and be awesome. It's taking me a while to write. I'm just going to set up this integral and let you evaluate it on your own, but or kind of halfway down with this one. 36 t to the 5th over 5 plus 4t cubed. And the integral of this would be 2e to the t squared. And then you would evaluate this from 0 to 1. that all good? Plug in your upper bound, plug in your lower bound, find the difference. All right, problem 2. Given f equals 2x sine y plus 6e to the 2x, comma, x squared cosine y minus 1 over y squared plus 1, and curve C parameterized by the following. Find the work done by f along the curve C from t equals 0 to t equals 1. What should you, if you came to my review yesterday, or not yesterday, but last week, and you watched the video, you always know that you should always check what first. Check to see if what is what. If what is conservative. F is conservative. Is f conservative? Let's quickly check. Let's go and write the vector field up at the top. We have 2, okay, brushes, 2x cosine y plus 6e to the 2x, comma, x squared cosine y minus 1 over y squared plus 1. What is the derivative of the left hand, or the first component, with respect to y? What do I get? If I take the partial of this guy, wow, cool. Partial of this guy with respect to y, I get 2x cosine y, right? Oops, shit. Undo. Okay. Try that again. Partial with respect to y will give me, that's what I would do, an arrow. 2x cosine y. What's the partial of this guy with respect to x? What do I get here? 2x cosine y. This makes us happy that these match, right? Because these match, what can I say about the vector field? It's conservative. So that means the parameterization doesn't matter. All that matters is the value. So we have to find the what? Now that we know it's conservative, what are we going to look for? We're going to find that vector field's what? Potential function. Let's find the vector field's potential function by integrating the first component with respect to x. What is the integral of the first component with respect to x? Yeah, if I integrate 2x sine y plus 6e to the 3x, 6e to the 2x with respect to x, I would get, so let's say integrate this with respect to x now. We would get x squared cosine y, oops, x squared sine y. I can't just do this, right? Like I would with my hands on our whiteboard. Plus 3e to the 3x. What's the integral of this guy over here with respect to y? I would get x squared sine y. What's the integral of negative 1 over y squared plus 1? Arctangent y. So we're going to say minus arctan y. So what's my potential function? What would phi be? Hey guys. Probably get the packets over there. All right. What is phi? You take all the terms that are in common, or take all the terms, collect them all. Don't double count. So we have an x squared sine y. We have a 3e to the 3e to the 2x. 3e to the 2x. We already have the x squared sine y. We don't count it again. And we have a minus arctan y. So our potential function is x squared sine y plus 3e to the 2x minus arctan y. So the result of this line integral is whatever you get when you plug in the end point minus whatever you get when you plug in the beginning point. Okay? Let's figure this down here. Am I still on the screen down here? Okay. When I integrate, so the integral of f dot dr over c is the value of this potential function at the terminal endpoint. What is the terminal endpoint? A lot of people might say the terminal endpoint is 1, right? That doesn't make sense because the terminal endpoint isn't a time. The terminal endpoint is what you get when you plug 1 into your parameterization. In fact, you might see this. This is something you might want to write down. You might see this. Integral of f dot dr, this is like a true or false section, is phi of r of b minus phi of r of a. Now, if you've seen my video, what is all this saying? It's just saying phi of what? terminal minus 5 initial, right? Make sense? So what is phi of R of B? What is R of B? R of B is what you get when you plug in 1 into your parameterization. What happens when you plug in 1 in for, what is R of 1 here? Remember, parameterization is 4t minus t cubed comma sine of pi at t over 2. When I plug in 1 to that, I get 3 comma 1. Does everyone agree to that? Mm-hmm. And when I plug in 0 in for my parameterization, I get 0, 4 times 0 minus 0 is 0, and sine of 0, which is 0. So I get 0 comma 0. So I plug in 3 comma 1 into my potential function. What do I get? When I plug in 3 comma 1, I get 9 sine of 1. What is sine of 1? I have no idea. We leave it at that. Plus 3e to the 2x. When I plug in 3 for x, I get 3e to the 6. Minus arctan of y. What's the arctangent of 1? Pi over 4. So minus pi over 4. Minus what you get when you plug in 0 for both x and y. When you plug in 0 for both x and y, you get 0 plus 3 minus 0. And that's your answer. So for this first problem, or for problem 1, you want to write the 4 steps. For problem 1, put 4 steps required. You need the 4 steps. For this one, for problem 2, what are we using to evaluate this line integral? We're using FTLI, the fundamental theorem of line integrals. So you put FTLI under this guy. We're using FTLI, fundamental theorem of line integrals. We're using phi of terminal minus phi of initial. Cool? Any questions on this? If you have a question, just shout it out. Okay. Next page. Next page is really easy because we're using the fact that the vector field we're looking at is conservative. What's up, guys? We're using the fact that the vector field is conservative. Let's just say for the fact is, can you guys check to see if the vector field is conservative? Take the partial of the first component with respect to y, take the partial of the second component with respect to x, and you'll find that they are indeed equal. So it's conservative. Don't waste your time doing that. And it says, given that C is the intersection of the surfaces z equals x squared plus y squared and x equals y squared plus z squared. What are these surfaces? Yay! Nobody knows. No one ever knows. What are these surfaces? Anyone want to guess? Paraboloids. They're paraboloids. One paraboloid looks like this. One paraboloid opens up along the z-axis. You don't have to draw this, by the way. One paraboloid opens up like that. The other one opens up along the positive x-axis. So it looks like this. And there's an intersection there. Turns out the intersection is going to be something circular like that. There's going to be an intersection between these paraboloids. As you can probably guess, when they intersect, it's going to form a circle. Basically, the path over which this path integral, this line integral is being computed is what kind of curve? Something circular or elliptical. Whatever the case is, it's what? It starts where it ends, which means the curve is what? Closed. It's a closed curve. Which means you might see this notation. Anytime you're integrating over a closed curve, whenever you see integral and you see a circle around that, it's automatically telling you the curve is closed. It's not telling you to do anything different. It's just telling you the curve you're integrating over is closed. And whenever the curve you're integrating over is closed, the result of the path integral or the line integral is 0. If and only if what? Well, not if and only if, but if what? What? Yeah, if f is conservative. And again, what did we say earlier at the beginning of the problem? That f was what? Conservative. So f is conservative, the curve is closed. So what's the result of the line integral? 0. So for this problem, problem 3, you want to write f is conservative, c is closed, answer is automatically 0. All right. Oops. Green's theorem. We didn't talk about this in the first video. So Green's theorem says, here's what you do when f is not conservative, but the curve is closed. If the curve is closed, the integral f dot dr is equal to the double integral, ooh, we get into some double integrals now, of partial g partial x minus partial f partial y. Since our vector, so in our case, we're looking at the line integral x e to the xy dx plus xy dy. What is partial g partial x? What is the partial derivative of this guy with respect to x? This is g. If you want to, you can say that's f. That's g. What's partial g partial x? Okay, don't be shy. What's the partial derivative of x times y with respect to x? Y. Good job. Yes, Partial derivative of x e to the xy with respect to y. What would that be? No, with respect to y?
X squared e to the xy.
X squared e to the xy. Okay? And then we're integrating over d. Well, what is d? We know what c is. C is the curve that's enclosed, or C is the curve given by this graph over here. 0, 0, 0, 3, and 3, 3. So C is this curve. Oh, traversed counterclockwise. That's important. Green's theorem works if the orientation is counterclockwise. If the orientation is clockwise, if they say the orientation is clockwise, how do you change your answer? You put a negative in front, okay? But they say counterclockwise, so we're good here. We don't need to we don't need to multiply through by -1. So it's a counterclockwise orientation, but instead of integrating the vector field over the curve, we integrate this partial g, partial x minus partial f, partial y over the interior of this guy. So let's set up a double integral. We actually have this double integral. What do we guys want to integrate with respect to first? I'm going to integrate with respect to y first because I don't want to integrate that with respect to x. It's not going to be pretty. So we're going to do the double integral with respect to y first, then x. As I draw a line parallel to the y-axis, what do I hit first? Oh, it's been a while, hasn't it? As I draw a line parallel to the y-axis, what line do I hit? What line is this? X equals y, so I should say, what's my lower bound? What do I hit as I enter the region? X. Can't say y. Wait, yes, okay. What do I hit as I leave the region? Y equals 3. This is the horizontal line y equals 3, so I hit 3 as I leave the region. What's my leftmost value of x here? 0. What's my rightmost value of x? This coordinate is 3, 3. So my rightmost value of x is 3. So my bounds on x go from 0 to 3. And I'm going to do the integral of y minus x squared e to the xy over those bounds. Like that. Does anyone care to see the double integral done? You might have to do integration by parts for it. I think you will have to do integration by parts for it. Okay. If you want to see it done, let me know later. Or just ask me after the review's over. Say, hey, Andrew, can you show me how to do integration by parts because I forgot? Okay. So that's line integrals. Those are line integrals over vector fields. There will probably be a line integral over a scalar field, probably one of those, but there will probably be a lot of line integrals over vector fields. But now we're going to move on to surfaces. Surfaces are a little bit harder to do. All right. Curves are length, so they need one parameter. But surfaces possess area, so you need two parameters. Problem 5 says, give a parameterization of the surface of the parabolic cylinder z equals 6 minus x squared that lies above the xy plane, with x larger than 0, and between the planes y equals 1 and y equals 3. A lot of the best ways to do this, and this will work 85 to 90% of the time, is you can just say x equals u, y equals v. Z is whatever the function g of u comma v is. I always rush. G of u comma v. So all it means is you plug in for u when you see an x and plug in v when you see a y. So for this problem, we're going to do, as usual, as it says, x equals u, y equals v. Our equation that relates z to x and y is z equals 6 minus x squared. So instead of saying z equals 6 minus x squared, we're going to say z equals what? Z equals 6 minus what? U squared. This is a parameterization for the surface of the parabolic cylinder. However, of course, as I've said before, no parameterization is complete without description of its what? Bounds. We have to talk about its bounds. The easy bounds are some easy bounds with bounds for y or v. Bounds for v go from where to where? What's that? Speak up.
1 to 3.
1 to 3. 1 to 3 because we're told that the bounds for y go from 1 to 3, or y goes between the planes y equals 1 and y equals 3. And since y is equal to v, v goes from 1 to 3. How about the bounds for u? U are a bit harder. U's a bit harder. We at the very least know that u, since x is larger than 0, u must be larger than 0. Right? Doesn't it say x larger than 0?
Yeah.
And how do I know what the upper bound on u is? Is there an upper bound? Any idea?
6.
Not quite 6, you're close. What's that? Root 6. Remember, we want the part of the parabolic cylinder that lies above the xy plane. So we want to make sure we don't plug any values of x, or I guess u, that cause 6 minus x squared to be negative. So When does 6 minus x squared hit 0? Only when x is equal square root of 6, so u will go to square root of 6. Cool? This is a surface parameterization for the shape described. Cool? Now, there will be some crazier parameterizations, especially when we talk about spheres and cones. We'll talk about those surface parameterizations will be, not yet, but almost. Next one we're doing is a plane. This is something I've said before, that anytime you're given the equation of a plane where all the coefficients are positive and it equals a positive number, like in something like 2x plus 4y plus 3z equals 12. Look at the coefficients of x, y, and z. They're all what? Positive. Positive numbers. Yeah, I guess they could be anything. They're all numbers. Yes, they are all numbers. The coefficients are all positive. That's the important part. And the right-hand side is also positive. When that happens, the shape you get looks like this. Looks like a tetrahedron. Cool. Now, what's the x-intercept over here? Actually, no one gives a shit. All right, let's find parameterization. So, what's our standard, usual, go-to parameterization? X equals what? X equals u. Y equals v. Z equals whatever you get when you solve for z here. So z equals 4 minus 2/3 u minus 4/3 v. It's minus 4/3 v right there. Okay. Of course, no parameterization is complete without description of its bounds, so we have to talk about what the bounds are. That's going to be kind of hard because what are the bounds on u and v? It's going to be, we're going to project this into the xy plane and see what shape we get. The shape we get is this guy. Well, I don't feel my hand brushing up against it, but it must be the hair on my fingers or something. I don't know what's causing that to happen. Anyway, if we project this down into the xy plane, here's what you would see. Right? We'd see a downsloping line, and we need to figure out. Let's need to back up just a bit. So now let's actually answer that question. What is the x-intercept here? What value of x causes this to be 0? Who said that? Yeah, 6, right? What are you doing? You're basically setting y and z equal to 0 and solving for x. So what value of x causes 2x to equal 12? That would be 6. What value causes 4y to equal 12? That would be 3. What line connects the points 0, 3 to 6, 0? That would be the line y equals 3 minus 1/2 x. So let's go back over here and figure out our bounds. The bounds on y go from where to where? As I draw a line parallel to the y-axis, what do I hit first? I hit 0. What do I hit as I leave the region? I hit this line. The line for which equation is what? Ooh, I goofed. I'm not supposed to say y. What are my parameters? Not y, but rather what? U and v. So let's go back, let's say v instead. V goes from 0 to where? What line? V goes from 0 to where? It goes to 3 minus 1/2 u. Not 1/2 x, but 1/2 u. I have to make sure we say u and not x. Cool? And then what are my bounds on x? What's my bounds on u? What's my leftmost bound for u? 0. My leftmost value of x, you could say, is 0. What's my rightmost value of u? 6, right? It goes as far to the right as 6. So that's another parameterization for the parameterization of this plane. Cool? All right. Give a parameterization for the surface x equals 9 minus square root of y squared plus z squared that lies above the yz plane. Even I don't know how to do this. Okay, here we go. Shit. Okay, this is going to be hard. All right. We have... Probably should have thought this one through. Okay. Got it. Don't draw this. Okay, we're going to turn the page. I'll come back to that. Surface integrals over scalar fields. Step 1, parameterize. This is very much like the 4 steps for line integrals. Parameterize your surface. Don't forget that every parameterization needs bounds. Compute RU cross RV. This is probably one of the worst parts of doing these problems, that you have to do this RU cross RV crap. Think of it like a UV sub. Sub all that stuff into your integral, plug in for x, y, and z, and use ds equals as a conversion from x, y, and z, or from ds to du and dv. Integrate over the bounds of the parameterization. Note, the surface area of a surface S is given by the double integral of 1. Think about what did you do before? A double integral of 1, back in, for exam 3, what did the double integral of 1 give you? Area. What does the triple integral of 1 give you?
Volume.
What does the double integral of 1 over a surface give you? Surface area. Okay, problem 8. Compute 4xy ds, where s is the part of the plane, x plus y plus z equals 4 in the first octave. So we're going to go and draw that. So the axes, all the coefficients are 1, so we have, or not 1, but positive. They're also 1. So it looks like this. We're going to parameterize that surface doing our usual x equals u, y equals v, and z equals 4 minus u minus v. Cool? Let's talk about our bounds. Again, we're looking at what this would look like if we project it into the xy plane. So what would that look like? It would look like this. This would be 4. This would be 4. This is the line v equals 4 minus u. So our bounds for v go from 0 to 4 minus u. And our bounds for u go from 0 to 4. I'm half expecting one of these screens to just go pop or something and go like, guys, let's just run, let's get out of here. All right. So that's step 1. Step 1's done. We parameterized our surface. We found our bounds. Now we have to find RU cross RV. RU cross RV means we have to set up a determinant, I, J, K. I'm going to tell you a clever way to do this one in a second. We go through and take the partial derivative of all this thing with respect to u. So, ready? What's the partial derivative of x with respect to u? 1. What's the partial derivative of v, or v with respect to u? Or I should say y with respect to u? 0. Partial derivative of 4 minus u minus v with respect to u? Negative 1. We go again. The second row is what's the partial derivative of the entire thing, but this time going through with respect to y, or with respect to v. Partial derivative of this guy with respect to v? 0. With respect to v here? 1. Partial derivative of this guy with respect to v? Negative 1. Compute that cross product. You get 1i plus 1j plus 1k. Okay? This shouldn't surprise us, though, and in fact, anytime you're looking for the normal vector to a surface of a plane, you can just take the what? This goes all the way back to exam 1. What's that? Let's get on the right track. Use another code word.
Coefficient.
Yes, they're the coefficients. We have x plus y, not the same thing. I don't know, not the same thing. What are the coefficients of x, y, and z here? 1, 1, and 1. So unsurprisingly, the normal vector to our surface of the plane should be 1, 1, 1. If I give you the plane 3x minus 4y plus 7z equals 11, give me a normal vector to that plane. 3, negative 7, 3, negative 4, 7, right? Cool? So I don't need to do this whole ijk, at least not when it comes to planes, but for just about every other surface, you are going to have to do that ijk cross product. You might have also seen a formula that your professor might have given you that says this. I believe it says gx, gy, negative gx, negative gy, 1. Have you seen this before? That also works. It's the same thing. But in general, a more general form of finding a normal vector is by doing this ijk and putting the partial derivative of your parameterization with respect to u, then with respect to v, and evaluating that cross product.
Wait, where did you get the 3x minus 4?
I just made that up. That's make it up. That's imaginary. I just made that up. What happens when I do that? Okay. That has nothing to do with that problem. Okay. Oh, we're not done. What am I doing? Okay. So I do need to clear the board though. So we have 1, 1, 1. Don't forget our parameterization. No, I'm going to break something. All right, here we go. Step 3. What was our integral? It's the double integral of 4xy, right? Right? 4xy? Yeah. Someone help me out here. Okay, 4xy. X is equal to what? What's x equal to according to our parameterization? U. What's y equal to according to our parameterization? What? V. Okay. And then lastly, we have to multiply this ds term. But what is ds? ds is equal to the magnitude of RU cross RV du dv, or dv du, whatever order you want to do it in. What is RU cross RV? What was the magnitude of 1, 1, 1? Square root of 3. So we're going to replace this square root of 3 du dv. Let's actually not do du dv, because we actually found the bounds on v first, right? So let's do dv du. What are the bounds on v? 0 to 4 minus u. What are my bounds on u?
0 to 4.
0 to 4. That's your integral. Can I trust you guys to evaluate the integral on your own? No? Okay. Cool? So step 1 was parameterize. Step 2 was, remember, when you parameterize, you find your bounds too. Step 2 is find that RU cross RV, find that cross product. Again, you can use that formula, and again, a formula you might want to write down is negative gx, comma gy, negative gy, I should say, comma 1. But again, that only works when you have x equals u, y equals v, and z equals whatever the rest of your service is. Or drop your ijk, partial select to u, partial select to v, figure out that cross product. I prefer that, even if that's sometimes easier. Plug everything into your integral. So we had 4xy ds, but instead we have to replace x by u, that's according to our parameterization, replace y by v as per our parameterization, and compute the magnitude of that cross product RU cross RV. When I did so, I got root 3. Plug that in, you get root 3 du dv, or dv du. And then integrate over the bound specified, that would be step 4. We're not doing that, because it's a lot of work to do. Okay, cool, turn the page. Problem 9. Compute x plus z, where s is the, wait. What? Okay, I guess it's English, kind of. Where s is whose, okay, no. Where s is the surface, that must be what I meant to say, or s is the surface whose side, whoops. Okay. Compute x plus z ds, where s is the surface whose side is the cylinder y squared plus z squared between the planes x equals 5 and x equals 10. This is one of those surfaces where x equals something, x equals u, y equals v is not going to work. Okay? So whenever you have a cylinder, cylinders, you tend to want to use some sort of cosine and sine parameterization. What we're going to do here is, it's a cylinder that opens up along the x-axis. Let's get some blue here, let's get some green. I'm only putting the quarter cylinder there. So that's kind of a quarter cylinder, kind of like a bread box looking shape. It's supposed to go all the way around the x-axis, it's supposed to wrap all the way around, think of like a, a paper towel tube or something. But we only want, oh actually no, we want the whole thing. Shit. Well, it doesn't matter. Where do we want to be? We want to be on the surface of the what? We want to be on the surface of the cylinder. The cylinder has what radius? What's that? The surface has radius. The surface of the cylinder has radius 2. So that means y and z are going to be 2 cosine u. Let's say theta. And 2 sine theta. Now I get this question all the time. Andrew, why is it not y equals 2 sine theta and z equals 2 cosine theta? Because it doesn't fucking matter. You'll either trace out the cylinder this way, or you'll trace out the cylinder this way. Doesn't really matter, as long as you trace out one revolution from the cylinder. So we have y equals 2 cosine theta and z equals 2 sine theta. Why do we say r sine theta and r cosine theta? Right, we're on the surface of the cylinder. We want to be fixed on the surface. We don't want the radius from the x-axis to the surface of the cylinder to vary. We want to be on the surface of the cylinder. Yeah.
When you were talking about tracing the cylinder one way or the other, does that relate at all to when you reverse the direction that you're going?
Okay, so in general, this is a good question, and you might something we want to write down. When you reverse the direction of a parameterization for an integral over a scalar field, whether it's a surface integral over a scalar field or a line integral over a scalar field, reversing the parameterization order doesn't change the value of the integral.
So it's just a vector field when you switch it?
Yes, if we switch the order over a vector field, we will have to negate their answer. Cool? We'll see that a little later, especially for surface integrals. Cool? How about x? Well, it doesn't seem. Is there any way that x relates to y and z? Is there any relationship between x and y here? X, y, and z. Or sorry. Is there any relationship between x and y or x and z provided anywhere in this problem? No, there's not. No relationship between x and y. There's a relationship between y and z, but there's no relationship between x and y, or no relationship between x and z. So guess what? X gets its own parameter. Think of it this way. How many parameters do we have so far? Before we put x equals x, how many do we have so far? No. How many do we have? We have one parameter. What is that parameter? What?
Theta.
Theta. It's theta. We need one more parameter, though. So, and it's not going to involve itself in y or z because we've got everything that needs to be described by y or z right here. So, guess what? X gets its own parameter. X. Cool? You can call it u or you can call it v if you'd like. But because there's no interaction between x and y or x and z, you don't need any sort of theta involved in that term there. What are my bounds on x?
5 to 10.
5 to 10. What are my bounds on theta? If I had said first octant, where I want only this quarter cylinder, I would say theta goes from where to where? 0 to pi over 2. But I didn't restrict that by saying first octant anywhere, did I? No, I didn't. So theta goes from where? 0 to 2 pi. I want to get one full revolution of this cylinder. Cool? Any questions on that? All right, that's our parameterization. Step 2 is finding RU cross RV. So here's I, J, K. When I say RU cross RV, U and V are general terms for the parameters using your parameterization, but we're not using RU and R. We're not using U and V. We're using what? Nope. What are my parameters? What variables do I see on the right-hand side of my equations? Theta and x. Let's go through and take the partial derivative of this guy with respect to x. What's the partial derivative of x with respect to x? 1. Partial derivative of this guy with respect to x? 0. Partial derivative of this guy with respect to x? 0. So again, this is going to be, if I had room for it, I'd say, here, we'll do it here. This is Rx cross R theta. Okay? What's the partial derivative of x with respect to theta? What?
0.
0. What's the partial derivative of 2 cosine y, or 2 cosine theta with respect to theta? Negative 2 cosine theta. Oops, shit. Negative 2 sine theta. And then we have 2 cosine theta. All right, let's do that. Yeah.
Does it matter what order you do it in? Like,
Nope. If you switch this, well, it turns out anytime you switch 2 rows into determinant, you negate the value of the determinant. But what are we doing? What are we going to do this in the end anyway? Yeah, magnitude, right? We're taking its magnitude, so it doesn't matter. So let's find this cross product. 0 times this is 0. 0 times that is 0. So we get 0i. 1 times 2 cosine theta is 2 cosine theta minus 0. That would be, as a middle term, so minus 2 cosine theta j. And 1 times negative sine theta is negative 2 sine theta k. What are you doing on time? What time is it right now? Here's the clock, right? 4:42. Too slow. Way too slow. All right. Wow, we gotta keep moving. All right. Magnitude. What's the magnitude of this guy? Square 0. What do you get? 0 squared is 0. Negative 2 cosine theta squared is 4 cosine squared theta. And square the negative 2 sine theta squared, you get 4 sine squared. When you add those together, you get 4 cosine squared plus 4 sine squared is 4. The square root of which is 2. So long story short. Let's put it up there. 2 du dv, or not du dv, but rather what are our parameters? Dx d theta. 2 dx d theta is equal to ds. Okay? It should be a capital S. Okay, let's set up our integral. What is the integral? X plus z, right? Is it x plus z? I don't have the paper up here. X plus z? X, what's x get replaced by? What was this parameterization? Get replaced by x. What does z get replaced by? 2 sine theta. And our conversion from ds to dx d theta is 2. So 2 dx d theta. What are our bounds on x? Oh shit. Okay, yeah, it's 5 to 10, not 0 to 10. 5 to 10. And bounds on theta, 0 to 2 pi. This integration is pretty simple. This is going to be x squared plus 2x sine theta. Plug in 10, plug in 0, or 5 from the difference. This is going to give up, oh, this should be a 4. 75. Then it's going to be, your answer is going to be 150 pi. Whatever your answer is, 150 pi. That's your answer. Cool? Okay. Next problem. Let's clear all this. I imagine if I got more practice with this thing, I'd probably be much better at it, but as it stands right now, it's kind of weird. Okay, this one's much harder. Compute the double integral 2z of the surface of S, where S is the part of the sphere x squared plus y squared plus z squared equals 49 that lies above the cone square root of x squared plus y squared plus 3. We are not going to want to use x equals u, y equals v, z equals whatever. Instead, we're going to use the following. All right, where do we want to be? We want to be on the surface of the what? Sphere. So the distance from the center to the edge of the sphere will be fixed, and it's fixed at what? What's the radius of that sphere? 7. So we're going to say x equals, we would typically say rho cosine theta sine phi, but we want to be on the surface of the sphere, so rho is fixed. Okay? What about my bounds on theta and phi? Does it say first octave or anything like that? Nope, so my bounds on theta go all the way around. What about my bounds on phi?
0 to 7?
Nope.
0 to pi.
Nope.
Oh, you said 5.
Phi.
Never mind. 0 to pi over 2?
0 to pi over 3. Who wants an explanation why? So let's draw a quick sketch here. We've got a sphere, a really ugly sphere, and then a cone. Okay? And we want this yarmulke right here, okay? We want that yarmulke, and we want the yarmulke that lies above what value of phi? Well, you have to know your known cone. Square root of x squared plus y squared over 3 is the known cone phi equals pi over 3. And because we're going straight up, that would be phi equals 0. So phi goes from 0 to pi over 3. Cool? That's step 1. That's our parameterization. Step 2 would be find RU cross RV. So let's put a step 1 here. Step 2. Or rather, yeah, R theta cross R phi. What's up?
If we don't know that, can we just plug in let z is equal to that squared thing into the other
And then solve.
and solve for it?
Won't be fun. Probably not. You should know your known cones. Let's just say that. Okay. I'm going to tell you this cross product is very, 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 very disgusting. Because if I go through and take the derivative of this guy with respect to theta, I'm going to get, my first row would be negative 7 sine theta sine phi, 7 cosine theta sine phi, and 0. My second row would be 7 cosine theta cosine phi, 7 sine theta cosine phi, and negative 7 sine phi, which then I'm doing some multiplication there with, and I'm going to combine a lot of terms. Here's what this boils down to, though. Let me just go and give you the answer. And in general, it will equal whatever the radius of your, let's just say radius, squared times sine phi. So you can take this to the bank and memorize it. The magnitude of your normal vector to the surface of a sphere, given that it's parameterized in terms of theta and phi, is equal to the radius of the sphere squared times sine phi. Okay, so we're just going to use that for free. All right, next thing is so this is going to give us a way to convert from ds to phi and theta or whatever. Step 3 is stuff that's all your integral. So we have the double integral of what? What is the double integral of? Read it to me. Double integral of what? 2z ds. So the 2 stays. What does z get replaced by? 7 cosine phi. And what does ds get replaced by?
49 rho squared.
What's that?
49 sine phi.
49 sine phi. And then what are our parameters? What do we say? D phi, d theta. Cool? Bounds on phi go from 0 to pi over 3. Bounds on theta go from 0 to 2 pi. Can I do this in my head? 7 times 49 is 343 times 2 is 686. But then over 2, so I should have fucked that up. Sine squared, phi, pi over 3 is 0, 0 to pi over 3. Pi over 3, sine of pi over 3 is root 3 over 2 squared is 3/4. 3/4 times 343. Then times 2 pi. Cool, that's our answer. 3/4, 343 times 3/4, what is that? Yeah, you have a question?
Yeah, for Z, why did you use 7 cosine phi instead of arranging the equation that they gave us to be Z equals?
Because we're using, okay, what do we want to be? So you're saying, is your question, why isn't it Z equals square root of x squared plus y squared over 3?
No, why isn't it Z equals 49 minus x squared minus y squared all squared?
Because I said for some surfaces, and this happens 10% of the time, you don't ever want to do that. If I said x equals u, y equals v, z equals the square root of 49 minus x squared minus y squared, it's not going to be as pretty as if you do this. You probably could do it that way, and it might not be that bad, but I don't think it's that pretty, and I try and avoid that. Cool? Try the other way. If you'd like to, try x equals u, y equals v, z equals square root of 49 minus x squared minus y squared, but then you take some derivatives, it's not as pretty. Is when you do it this way. Cool? So I think your final answer ends up being 343 times 4. Really? I have no idea. Okay. 343 times 3 is 1,029. 1,029 times 2. Shit. 2,058 pi over 4. Oh, but then it's over 2. 2,000. Okay, I don't care. All right. Problem 11. Find the area of the cone. This is kind of, obviously didn't leave enough room, but what would you do? Oh, area of the cone. Shit, never mind. So we have to change this all up again. Let's erase this. We want to find the area of the cone. So we're doing, what interval do I want to set up? I want to find the surface area, so I want to do what? Double integral of?
1 over the area.
1, there we go.
Or just 1?
No, just 1. Just 1. Double integral of 1 is surface area. I swear to God, if you go back one page, it tells you how to find the surface area. Yeah. No. The surface area of the surface of S is given by double integral of 1 ds, right? So we're looking for the surface area of this cone. Okay. What do I want to write here? You want to find a parameter. This is a little bit different. Where do I want to be this time? Do I want to be on the sphere? Where do I want to be? On the cone. So this time, phi is fixed. Why is phi fixed? Because where do I want to be? In general, where do I want to be? Where's the surface? The surface is the surface of the what? Cone. What am I? Okay. Look at problem 10. Problem 10 says S is the part of the what? Sphere. So where did I want to be? I wanted to be where? On the sphere. So I fixed rho. Because if rho is anything like 6.9 or 7.1, I would have been on the sphere. So I fixed rho to be 7. As we saw, our parameterization was 7 cosine something, 7 sine something, and so on, right? This time for problem 11, we want to be where? We want to be on the what? We want to be on the cone. The cone is defined by what variable? Rho, phi, or theta. Phi defines the cone. So what do we want to do? We want to fix phi, and phi is fixed to be what? Pi over 3. That's the pi over 3 cone. But we still use the same parameterization. We still say, by the way, you could do that, or you could do again, you could say x equals u. Some people are more comfortable with this, by the way. Some people just like saying, being consistent, x equals u, y equals v, z equals square root of u squared plus v squared over 3. But the computation might be a lot uglier. Computation can be very ugly. So if you can deal with the computation, when you do this cross product, doing the derivative of this guy with respect to u, kind of ugly, right? Then by all means go ahead and do that. But sometimes you can use this instead. So if you use the spherical parameterization, you would say x equals rho cosine theta sine phi. Well, what is phi? Phi is fixed to be pi over 3, so we say pi over 3. Then you would say y equals rho sine theta. This is obviously way too much for you to write, but the idea is you would do the same exact thing as you did before, but this time fixing phi as opposed to fixing rho. That's all I really wanted to say here. Is all really problem 11 is here to do is make sure you guys are paying attention to where you want to be. You want to be on the cone here, or you want to be on the sphere? You want to be on the cone. All right, let's just turn the page. It's not that important to do the rest of that. Plus, I didn't give you the room to do it. All right, orientation. The vector normal to the surface is computed using a formula n equals RU cross RV over the magnitude of RU cross RV. So that makes it what kind of vector? What's up? What? Nope. What? Yes, it's a unit vector. Anytime you divide a vector by its own magnitude, it makes it a unit vector. The positive orientation means that the z component is positive. So compute the normal vector to the surface of the sphere, x squared plus y squared plus z squared with negative orientation. Should have done this one. Let's just do it. Use it. Let's solve for z like we would have done in the last problem. So z equals the square root of 25. We're going to see how gross this looks, but it's fine. X equals u, y equals v. Okay? So, I, j, k. Let's go through and take the partial derivative of this guy with respect to u. What's partial derivative of x with respect to u? 1. Then we get 0 here. Then we get negative u over the square root of 25 minus u squared minus v squared. And the second row is 0, 1, but then it's negative v over the square root of 25 minus u squared minus v squared. So if you take that cross product, let's do it over here. Take that cross product, you get negative u over square root of 25 minus u squared minus v squared, comma, great, not enough room to write the rest of this, negative v over square root of 25 minus y squared minus u squared minus v squared, comma what? Let's see how I can do this. This would be really cool if I can do this. All right. Damn it. Yeah. Cool. All right, and then comma, what's 1 times 1? 1 times 1 here, right? 1 times 1 minus 0 times 0, so 1. Is this the positive orientation or the negative orientation? How do you know? Z is positive. Z is a positive 1, right? If I wanted the negative orientation, just negate everything. Duh. All right, let's do one more on orientation. Compute the normal to the surface. Z equals 9 minus 2x squared minus 3y squared with a positive orientation. Oh, sorry. The question in problem 12 said what? Wants what? Negative orientation. I goofed that up. So this is not my answer. My answer is actually the same thing, but positive u, positive v, negative 1. That's the answer to this problem. Make sure you're paying attention. I just overlooked it, like some of you might just on the test, and we hope that doesn't happen. Don't just overlook. Make sure you're paying attention to what orientation we're looking at. We want the negative orientation. So this 1 points down. We negate everything. All right, problem 13. Compute the normal to the surface. Actually, go ahead, give it a try yourself. I'm going to write it on the board while you guys do it. But give it a try yourself. That's what I got for my normal vector. Anyone else get something different? Is everyone good on that?
Yeah.
Cool. All right, next question. Now we're doing surface integrals over vector fields. Yay, exciting. This is what maybe 10% of your test is going to be on. And then theorems that pertain to them, like Stokes' theorem and divergence theorem. So problem 14 says, set up the integral that represents f dot ds, where f is 2y xz x squared, and the surface s is the part of the plane x plus y plus 2z equals 2, oriented in the positive direction. Step 1, let's go and find a parameterization for our plane. X equals u, y equals v, z equals what? 1 minus 1/2 u minus 1/2 v. don't forget, you probably draw a plane here, like this. You'd find the projection of what this guy looks like in the XY plane. And that would be the equation V equals 2 minus x. 2 minus uw, or 2 minus u rather. Cool? So V goes from 0 to 2 minus u, and u goes from 0 to 2. Does anyone have any, by the way, is anyone lost to me doing this? Raise your hand if you're lost to me doing this, like this is the third time. I'm still losing it here? Okay, what part am I losing you on? These bounds?
I just didn't see the equation 1 minus 1.
Oh.
Maybe it was just the transfer.
You just solve for z.
Yeah,
so you just subtract the x over, subtract the y over, and then divide by 2, so you get 1. 2 minus 2 divided by 2 is 1, and then you get 1 half u, 1 half v. Does that make sense? Yeah. I just solved for z in that equation. Okay. Stop start. Step 2, we want to find RU cross RV. Why don't I have to waste my time with this? Or what is the answer really quickly? What's that? 1, 1, 2. I don't have to compute a cross product because, again, what surface is this? This surface is rare, or a unique surface in that it's a what? A plane. So the normal vector to the plane is merely whatever the coefficients of x, y, and z are. The coefficients of x, y, and z for the equation in the original plane were 1, 1, and 2, so my normal vector is 1, 1, 2. Is it oriented the right way? Yeah, so we're good. So what that means is, step 3 is double integral of f dot ds is the same thing as double integral. What is f? F is the vector field 2y, xz, x squared. What is 2y? Remember, we're going to replace every instance of x, y, and z by its parameterization. So instead of 2y, we have 2 what? V. 2v. What is xz? Xz would be u times 1 minus 1 half u minus 1 half v, comma, x squared. Well, x is equal to u, so we have u squared as our last component here. And this is supposed to be dotted with what? ds. What is ds? This guy is ds. So we're going to dot it with 1, 1, 2. Step 4, going to integrate after we simplify. But tell you what, on the exam, it's going to very likely be which integral represents the surface, blah, blah, blah. So you're going to look for any answer choice that looks like this. 2b, we have plus u minus 1 half u squared minus 1 half uv plus 2u squared dv du. And then what are my bounds on u and v? We have them up there in the upper right-hand corner. V goes from 0 to 2 minus u, and the u goes from 0 to 2. All right, that would be the setup. You can integrate it on your own, but probably not that fun to do. Does everyone have any problem with that setup? Does anyone have any problem with the dot product? Does anyone have any problems with me plugging this in? This one used to be 2y, u, xz, and x squared, dotting it with the normal vector. Taking a picture? No. You're taking a picture of your eyes? What the hell's going on? I also use my phone like this. I'm not taking a picture of you, I swear. But it looks like it. Okay, we good? Is everyone happy with that? Yeah.
Can you go over the
projection here?
Not well, I understand like the image and everything.
What?
But the UV, like the bounds again.
Yeah. The UV bounds? The projection of this guy into the xy plane looks like this. When I draw a line parallel to the y, or the v-axis, you say, what do I hit first? V equals what? 0. Then what do I hit?
0, and then line
2 minus x or 2 minus u, right? What's my leftmost value of x here? Or 0 for u, rather. What's my rightmost value of x? 2. All right, press for time, press for time, press for time. All right, 1 hour is up. We have an hour to go. What do we have left? Some of these I just might end up skipping because I'm running out of time. Problem 15, compute f dot ds, where f is x, comma y, comma z squared, and s is the part of the cylinder, x squared plus y squared lies below the plane, y equals z, and above the xy plane, and oriented to the positive direction. Okay? Here's what we're going to do. Notice, oh shit, even I don't know how to do this. All right, and I wrote it. I wrote the damn thing. We see a cylinder, so we're going to say x equals, oh, what do we want to be? S is the what? S is the part of the what? Cylinder, right? So where do we want to be? We want to be on the cylinder. So we're going to say x equals 3 cosine theta, and y equals 3 sine theta. That would give us x squared plus y squared equals 9, right? What's the value of z then? Shit, this is not good. This is bad. That's very bad. Z is its own, there we go, that's right. Z would be its own parameter, right? That's what happened before. Anytime we have a cylinder, we used up theta for x and y, but then we have to, z gets its own, the remaining variable gets its own parameter. So z gets its own parameter. Remember last time we used y and z were sine theta and cosine theta, or 2 sine theta is 2 cosine theta. Well, this time, z is the lone man out, and he gets its own parameter. Cool? All right.
Does it just matter like which way the cylinder is going, which axis? Like if it's going up on the z-axis versus it's going out on the
It is oriented up. It's opening upward along the z-axis. Looks like this.
And so you just change that based on which way.
Huh? So it's got a positive orientation, which means it opens this.
So whatever
Points out.
axis the cylinder's on is the axis that's set equal to the same.
Yeah, that's a good way of saying it. Yeah, his question was whichever axis the cylinder is centered on is the variable that gets its own parameter. So this is an Jesus, the words. This is a cylinder that opens up along the z-axis, so z gets its own parameter. Z equals z. Okay. What are the bounds on theta? This one's kind of hard. It says above the xy plane. So theta goes from 0 to pi. Let's talk about y briefly. Why would theta go from 0 to pi, not 0 to 2 pi? Because remember, this is cut by a plane, y equals z, which looks like this. Okay? It's hard to draw. Anyway, here's what we're getting here. We're getting this surface right here. Notice where does this sit relative to the line y equals 0? Where does it sit? It sits on this side, right? Does everyone see that this shape here sits on the for these values of theta? Whereas if we're over on this side, what's the value? Where's the plane? Where does the plane end up being? Below where? Okay, I'm losing everyone here. It's below. Everyone see this plane is below the xy plane now? If you go too far to the left, that would be for the values of y for which, or values of theta for which we have third and fourth quadrant theta values. So theta only goes from 0 to pi. It's hard to see. But think of it this way. Remember, if you said, remember that we have the equation y equals z in here, right? Y equals z. What's the value of y? It's 3 sine theta. When is sine theta negative? What values of which values of theta is sine theta equal to? Jesus. What value of theta is sine theta negative? Third pi to 2 pi, right? So pi to 2 pi aren't going to be included because we're going to get negative values of z. And where are we supposed to be? Where does it say we're supposed to be? Well, the part of the cylinder that's where? Above the xy plane. Right? All right. Now what? Let's find RU cross RV. It's kind of hard. I, J, K. RU would be, or R theta, I should say, would be negative 3 sine theta, 3 cosine theta, and 0. And we have 0, 0, 1. If we do this cross product out, we get 3 cosine theta, comma, 3 sine theta, comma 0. So this might be a little confusing because is this the positive orientation like I want? Weird, right? Because we have 0 and the z components. So we're like, I have no idea if this is the positive orientation or not. When we're talking about kind of a closed surface, positive orientation means pointing outward. So Positive orient. So this is let's draw. What do I do here? Let's draw this. Let's draw a sphere. Positive orientation means outward. Negative orientation means pointing inward. Okay? So this is positive orientation. That's negative orientation. Okay? So we want to point outward from this cylinder. Let's look at the cylinder kind of top-down view. Cosine theta, so for a point like this guy at theta equals, I don't know, pi over 4, we want a vector that points this way. Is 3 cosine pi over 4, 3 sine pi over 4 going to point that way, or is it going to point in? What's the cosine of pi over 4? Positive or negative? Positive. What's the sine of pi over 4? So it is indeed pointing outward, so we're not going to negate this. This indeed points outward. So this is the correct RU cross RV. Lastly, we need to set up the integral, so we have, right? This is the integral x, y, z. So we have, what is x? X is 3 cosine theta. Y is equal to 3 sine theta. And it says, comma, z squared. Z is equal to z. So we have z squared. And we're supposed to dot this with 3 cosine theta, 3 sine theta, comma, 0. Double integral. When you perform that dot product, what do you get? What's 9 cosine times, or what's 3 cosine times 3 cosine? 9 cosine squared. What's 3 sine times 3 sine? 9 sine squared. So we have 9 cosine squared plus 9 sine squared is what? 9. So we have 9 d theta dz. Theta goes from 0 to pi. We didn't talk about bounds on z. These are actually where it's kind of hard. Z goes from 0 to 3. Let's say that. Why do I know z goes from 0 to 3? What's the highest value that y takes on? 9. Careful. Y? 3. And because y is equal to z, what's the highest value that z takes on? 3. So whatever that integration is gives you your answer. Okay? We are not going to be able to do number... Oh yeah, we are have to do 16. All right, 16. Let's do it. Thankfully, I give you a lot of the work that needs to be done for it. I give you the normal vector. Find the flux of the vector field. By the way, anytime you see the word find the flux of the vector field, all that means is find f dot ds. That's all. So find f dot ds for the vector field given. The vector field is negative y, comma x, comma 2z. Across the surface of the sphere, whose equation is x squared plus y squared plus z squared, oriented in the negative direction. Where do we want to be? We want to be on the surface of the what? We want to be on the surface of the sphere, so we're going to fix what? Fix rho. What's our radius of the sphere? 4. So 4 cosine theta sine phi, comma 4 sine theta sine phi, comma 4 cosine phi. What are my bounds on phi and theta? I don't think I have any restriction here. Nope, no restriction. So phi goes from 0 to pi. Those are full bounds for phi. And we want the full bounds for theta, 0 to 2 pi. Okay, now, this is, what the hell's going on here? This is my parameterization. Okay, let's fix this. Say r of t, or r of phi theta. There we go. That's my parameterization, right? Step 2. Find r phi cross r theta. Thank God we don't have to do that because I gave it to you. Everyone see that r phi cross r theta, r phi cross r theta is, yeah, the positively oriented normal vector to the sphere x squared plus y squared plus c squared equals c squared is equal to the thing down there. So we're going to have double integral of f. What is f? F is negative y, so it would be negative 4 sine theta sine phi, comma, positive x, that'd be 4 cosine theta sine phi. I'm going to slow this down after in a second just to catch you guys up. And then we have 8 cosine phi. And we're supposed to dot this with the mess 16 cosine theta sine phi, comma, 16 sine theta sine phi. Oh shit, there's a sine squared here. Sine squared phi, comma, 16 cosine phi sine phi. This is a giant monstrosity to dot product out. At the very least, so I do want to come back and make sure you guys understand where I got this. What is this?
That's from the original function.
Well, what letter is this? What variable is this?
Y, negative y.
It's negative y, right? It was negative y, comma what?
X.
X, comma
2z.
2z. And together this makes what? What is this?
The vector field.
Which vector? Yeah, the vector field, which is called f, right?
F.
What is this guy?
That's R.
Not r,
DS.
ds.
R, ds. Okay.
So this is indeed the original f dot ds. It's always important to see where you're coming, where you're starting from, where you're going, and how you got there. Okay. Perfection is a lot of little things done correctly. Okay. So multiplying this out, here's what you're going to get. Everyone, look up for a second. Negative 4 sine theta sine phi times 16 cosine theta sine squared phi would be negative 64 sine theta cosine theta sine cubed phi. 4 cosine theta sine phi times 16 sine theta sine squared phi would be positive 64 sine theta cosine theta sine cubed phi. So what happens to those two terms? Yeah, they cancel and give you 0. So the mean result of this integral is just 8 cosine phi times 16 cosine phi sine phi. So 60, oh shit. I keep want to go to my laptop to undo. 8 times 16, 128 sine phi cosine squared phi d phi, d theta. Oh, okay, no. D phi, d theta. Oh, I can do this. Not quite. D phi, d theta. Okay? So we have 128 sine phi cosine squared phi d phi, d theta, and this is a result of, when I do the dot product out of f with ds, a lot of stuff cancels. In fact, the first term cancels with the second term, and then my last term is just 8 cosine phi, right, 8 cosine phi? 8 cosine phi times 16 sine phi cosine phi, which gives us this. What's the integral of 128 sine phi cosine squared phi with respect to phi? It'll be 128 cosine cubed phi, negative at that, over 3, evaluated from 0 to pi. Why from 0 to pi? Because this is my bounds on what?
Phi.
And I just integrated with respect to phi, didn't I? So I plug in pi, I get cosine, what's the cosine of pi? I know this is really boring. Negative 1, right? Negative 1 cubed is negative 1 times negative 128 is positive 128, 128 over 3, minus what you get when you plug in 0. So minus negative 128, what's cosine of 0? It's 1, 128 over 3. That's going to give us 256 over 3. We integrate that result. Integral 256 over 3 with respect to theta. Oops, not a double integral. From 0 to 2 pi. And that gives you 512 pi over 3. 512 pi over 3. Really, a lot of work for a tiny little bit of answer. We're going to see how this answer can be really easily computed in the divergence theorem on the next page. Yeah.
Good question. How did you come up with the bounds phi? And how can we like?
How did I get my bounds for phi? Did I only want a certain part of the sphere, or did I want the whole sphere?
You only wanted some of it.
How? Which part of it do I want?
Well, it says oriented in the negative.
Oh, by the way, it says oriented in the negative direction, right? There's one thing I forgot. Oriented in the negative direction, so I have to change my answer. This kind of goes back to your question. Or someone had a question about orientation. I forget. Yeah, it was you? Yeah, so it's the negative 512 pi over 3 because it's oriented in the negative direction. It points inward. But no, it doesn't want any part of the sphere. It wants the whole sphere, doesn't it?
Oh, yeah, yeah.
So theta goes from 0 to pi, phi goes from 0 to pi. Cool?
So phi normally will go from 0 to pi if it's not specified?
Yes, exactly. If it's not specified, we want the whole sphere.
All right.
Okay. So negative 512 pi over 3, and there's a lot of work to get there, right? It wasn't just this page, but also in the work video over here on the left page. But the divergence theorem makes this a lot easier. What does the divergence theorem say? The divergence theorem says that if the surface you're talking about encloses a region, instead of doing a lot of work that we just did, we can do the following. Instead of doing f dot dr, we're going to do the triple integral of the divergence of f. What is the divergence of f? Remember, the f is this guy over here. It's negative y, comma x, comma 2z. Okay? What is the divergence of this vector field? What's the partial derivative of this with respect to x? 0. What's the partial derivative of this guy with respect to y?
0.
What's the partial derivative of this guy with respect to z? 2. Okay, so it's the triple integral of 2 dv over the region E enclosed by the surface. What does the triple integral of 1 give you? Volume. And what's this shape we're looking at? What? A sphere. What's the volume of a sphere?
4 over 3 pi r cubed.
4 over 3 pi r cubed. What's the radius of the sphere?
4.
4 cubed is what?
64.
64. So we have 4/3 times pi times 64, which is 4 times 64 is 256 pi over 3. Okay? That would be the volume of the sphere. That would be the triple integral of 1. But what are we doing? We're doing the triple integral of what? 2. So what's the triple integral of 2? Double that. So we're going to double that because it's the triple integral of 2. 512 pi over 3. Don't forget, though, that our surface is oriented which way? Orientated. Negative. It's oriented negatively, so we get negative 512 pi over 3. What way was easier? This way, or the work, all the work we did in the previous page?
This way.
This way was a lot faster. You're going to find some problems that the divergence is really easy to compute, and the surface you're integrating, or the region you're integrating over is really small. Pretty simple. How much time do we have? Oh, God, not enough. Just not enough. Problem 18. Compute the flux of F equals across the surface of the cube. Oh, this is great. This is perfect. Okay, so notice that the surface of the cube would be, how many sides does this cube have? Can I go back anymore? How many sides does the cube have?
6.
Good job. Okay. 6, right? So what that would mean is we'd have to compute a flux integral over, let's just draw it. We have to compute a flux over this surface, 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 a flux that. We're going to do this instead. We're going to instead say, because the surface encloses the region, we're going to use the divergence theorem. So the divergence theorem says that instead of computing this flux over, remember we have to add up all those fluxes. So whatever flux contribution you get from one side, plus the flux from the second side, plus the flux from the third side, plus the flux integral from the fourth side, all the way to the sixth side. That'd be a lot of flux to do. Flux that, right? So what we're going to do is the triple integral of the divergence of f. What is the divergence of f? What is the divergence of y cosine z? Or what's the partial derivative of y cosine z with respect to x?
0.
0. What's the partial derivative of y squared sine, or what's y squared plus z sine x with respect to y? 2y. What's the partial derivative of x tangent y with respect to z? So we have just the triple integral of 2y dx dy dz. What are my, oops, whatever, doesn't, the order doesn't matter, they're all constants. What are my bounds on x, y, and z? They're all what?
0.
So the integral of this with respect to x is 2yx, plug in 1. The answer is 1. The answer ends up being 1. Cool? Compute the flux of f equals 3xe, comma e to the xe, comma ln of x squared plus y squared across the part of the paraboloid. Z equals x squared plus y squared that lies under the plane. Z equals 4, oriented in the positive direction. Okay, this is a bit tricky because it's what the divergence theorem says. You need to use the divergence theorem whenever the surface encloses the region. God, I hate that. Let's do orange. But the surface described here doesn't enclose a region. It's just a what? A paraboloid. So it's like a bowl. Okay? It's just a bowl. It's just this piece down here. It is not the lid. The lid's not with it. The lid is not here. But let's for a moment pretend that it was. Let's for a moment say that the lid was there. So pretend the lid's there. That would mean the divergence theorem would give us what? It would give us the flux across this surface, which we'll call S1, plus the flux across this surface, which we'll call S2. Now again, for the purpose of this problem, S2 is not really there. Yeah?
What's flux mean?
It's this.
have units?
No, well, it can be like unit volume per second usually, or unit volume per second. Yeah. Think about a river. Like a really fast-flowing river has a lot of flux. Like through a given point, picture a net. If water's flowing really fast through a net, there's a lot of flux there. It's a lot of water moving across the net. Versus, and this applies to a lot of you who are taking, anyone in Physics 2 right now or taking Physics 2? So the idea of magnetic flux or electric flux was the amount of electric current passing through a certain point. Not current, but charge, or the field that you can feel through a certain net. Cool? But don't worry about that. It just means we have to compute the flux that is F dot ds for this guy and F dot ds for this guy. So this is going to be S1 plus S2. Okay? And then F dot ds. Now remember, the question only wants this. The question only wants this guy. Right? We don't want F dot ds over the lid. We just want over S1. So here's what we're going to do instead. We're going to find, according to the divergence theorem, what would this give us? What's the partial derivative of 3xz with respect to x? 3z. Partial derivative of e to the xz with respect to y? 0. Partial derivative of ln of x squared plus y squared with respect to z? 0. So my divergence is 3z dv. And because I just want what's in the box here, I just care about this guy, I'm going to subtract F dot ds over S2. Now you might be saying, well, Andrew, how's that any simpler? I've gone from computing one double integral over the surface of the paraboloid to computing a triple integral and a different surface integral. Well, here's what tends to happen. This double integral tends to be a lot easier to compute because, hey, look, what shape is this? S2 is just a what? A circular disk. That's really easy to compute a flux over that because the parameterization for that's really easy. We might say the parameterization is r cosine u, or r cosine theta, r sine theta, comma. Where does this exist? Where does this disk exist? In what plane? Z equals 4. So comma 4. So really quick and easy parameterization for that surface. Ru cross Rv would be the normal vector R, stuff like that, and from there it's really easy to compute. As opposed to doing this guy. If you do the flux across this guy, you're going to have a nightmare trying to compute it. Especially because, not to say nothing of the fact that, look at the vector field. E to the xz, ln of x squared plus y squared, all that's going to go away because, watch what happens. We're going to go find, I'm going to go ahead and tell you right now that Ru cross Rv is, let me do this in my head really quick. Cosine theta, sine theta, 0. So, this would lose my mind here. Lose my mind. Give me a second, guys. I, j, k, r cosine theta. Nope. Negative r sine theta. R cosine theta. 0. Now the partial with respect to r gives us sine theta, cosine theta, sine theta. So you get this, you get r, 0, 0, r. Your normal vector of that surface is 0, 0, r. By the way, that makes sense. Look at this disk right now. The normal vector points strictly where? What direction? Straight up. Is there any x component? Is there any x motion or y motion here? No, it's strictly z motion. So it makes sense that our normal component is 0, 0, r. So plugging this into our flux integral, we get, what was this? F is 3xz, e to the xz, comma ln of x squared plus y squared. All right? What is 3xz according to our parameterization? 3xz would be r cosine theta, r sine theta, 4. So that would be, let's do it this way. Let's just say xz. We can plug into that later, but not do that right now. E to the xz, comma, ln of x squared plus y squared. What is x squared plus y squared according to this parameterization? What's r squared cosine squared plus r squared sine squared? It's going to be what? R squared. So we get ln of r squared. And we want to dot this with our ds. Here's the nice thing about this, though. What happens when I dot this with this? 0. What happens when I dot this with this? 0. So I just get ln of r squared times r. So I get double integral of r ln of r squared, which will compute using integration by parts, dr d theta. R goes from, this is 0 to 2, the radius of that circle is 2, and all the way around, 0 to 2 pi. So let me break this down for you. Do you have to have a enclosed region to use divergence theorem? The answer is no. What you do is you say, okay, I want the flux over S1. I'm going to pretend there's a lid there. So the divergence theorem would give me the flux across the bowl plus the flux across the lid. So divergence theorem gives me the flux across the bowl plus the flux across the lid. What does the problem just want, though? It merely wants the flux across the what? Across the bowl. I don't want it across the lid. So I subtract the flux across the lid over from the left, and I compute these two integrals, and I'll be done. Of course, it seems like a lot more work than it's worth, right? It seems like you're better off doing the first integral to start with, but trust me, 3xz and e to the xz, doing the dot product, those would be very unpretty. Yeah?
For the other surface integrals we did previous to divergence theorem does not apply to those.
Right, because those didn't enclose a region. And in general, you don't always want to use the divergence theorem unless it's really easy to, either you have a region that's enclosed, or it's really easy to enclose the region, as it is in this case. You can just put a lid there, namely the plane z equals 4, right? Okay, there's not enough time to do Stokes' theorem, sorry guys, but there is time to do the true-false section. So we can come back to Stokes' theorem later. I'll probably put up something or type something up to tell you what to do for Stokes' theorem. Let's move on to true or false, though. Okay? Sorry, drawing on this board I never thought would take so long. I'm having to kind of dance around, so I know it's probably really amusing for you. Let's do the true or false, though. All right. When computing a line integral over a scalar field, reversing the direction of parameterization of the curve negates the value of the integral. True or false? False. Why? Right. Over a scalar field, reversing the direction of parameterization doesn't matter. Doesn't matter if you reverse. If you do, so you might see on the test true or false. Wow. What is that? How does that happen? Integral of f ds, this is over a scalar field, this is a line integral of a scalar field, they might say equals negative integral f ds if we negate c, c being the reverse direction, to which you say no, false. Because for scalar fields, it doesn't matter. However, the second question says true or false. If I'm doing f dot dr over a curve C, then I get the negative result if I negate the curve for f dot dr. And that is true. Okay? Next one, number 3. The integral, the line integral of 3x squared y squared, or sorry, 3x squared y cubed dx plus 3x cubed yz dy over curve 1, and the same integral again, but over curve 2, will have different values if C1 is a parabola connecting 1, 1 and 3, 9, while C2 is a line segment connecting 1, 1 and 3, 9. True or false? Why? That's not enough information. That's not enough reason. Because it would be false. The answer would be false if, say, it said y to the 4th. If the first guy said y to the 4th in both integrals, then it'd be wrong. Why? It's yes. The vector field here is conservative. Take the partial. What's the partial derivative? I want to take the partial derivative of the 3x squared y cubed with respect to x. What do you get? Sorry, I meant to say with respect to y. So you get 6x squared y squared, right? Take the partial derivative of the 3x squared y squared, 3x cubed y squared with respect to x. Yeah, right. 9. Yes, 9. There we go. And we get 9x squared y squared there as well, right? So it is a conservative vector field. So now you can say what you said. What did you say before? It does. The path you take doesn't matter, so long as you know that what? What? What's conservative? No, not everything. If what's conservative? The vector field. Is the vector field conservative here? Yes. So the path doesn't matter. It doesn't matter what path you take to get from 1, 1 to 3, 9. Cool? So it's not enough to say the path doesn't matter whenever you do any line integral. It has to be a conservative vector field.
So then it's false, right?
So that's why it's false, right? They will have the same value.
Okay.
Suppose f is a two-dimensional vector field. If f dot dr equals 0 for every circle drawn in the coordinate plane, then f is a conservative vector field. This is a tricky question. What this is saying is, no matter what circular path you take whenever you integrate this guy, you always get 0. No matter what circular path you take, you always get 0. So is F a conservative vector field? The answer is no. What would it mean for it to be conservative? If for every closed path you got 0. If you got 0 for every closed path when you did the line integral, what would that say about the vector field? 0. What closed path is this question only asking about? Circles. But there are plenty of other closed paths, right? We can look at this is a closed path, right? So the integral might be 0 for every circle you draw, right? But then here's this shape. This, I don't know what this is. A potato. Potato that fell over. I don't know what it is. But basically, that shape is not a circle, but the path integral could be non-zero for that. So it's not necessarily conservative. All right, next one. 3y squared plus cube root of e to the x plus 1 dx plus 4x minus arc sine of 0.1 y cubed plus 0.1 y dy is computed over one revolution of the curve with equation x squared minus 4x plus y squared equals -1. What theorem should we use to compute this integral? Any guesses? What?
Green.
Yeah, Green's theorem. Why?
I just guessed.
Yeah, I know you did. Why Green's theorem?
Px and dy are attached to something.
It's a good try. Green's theorem works when... Why do we use Green's theorem? Think back to the first video. We use Green's theorem whenever the vector field f is not what? Conservative, but the curve we're integrating over is closed. Why is this a closed curve? Why do I know this is a closed curve?
One revolution of the curve.
That kind of gives it away, doesn't it? The fact that I say one revolution, yeah. If I didn't say one revolution, how would I know that the curve x squared, where is the goddamn curve? Minus 4x plus y squared equals -1. How do I know that's closed curve? What shape is that? It's a circle, so I know it's closed, right? It's a circle, it's closed, and the vector field itself isn't conservative, but it's a closed curve, so I might want to use Green's theorem because I use Green's theorem whenever my curve is closed, but my vector field is not conservative. Stokes' theorem says that curl f ds dot ds is equal to integral. So everyone look up for a second. Stokes' theorem, if you look at Stokes' theorem, it says this. Oops, I goofed. It says curl of f. And it equals integral f dot ds over c. Okay? So this looks almost exactly like what we have in this middle of the page problem. Stokes' theorem says the double integral of s over curl of f dot ds is equal to f dot ds over c. But it doesn't say that, does it? What does it say? Looks like partial derivative of s, doesn't it? Has anyone seen Kieran use this notation before? What it means is the boundary of s. So this, whenever you see, it means the boundary of s. It doesn't mean partial derivative. Cool? So when we're talking about a surface, think about like a bowl. Here's the surface. The boundary is this guy here. That's C. This guy is S. How do I know C is the boundary? Think about it being an ant on the surface of this bowl. If you're on the outside of the bowl, you're crawling up, and then what happens when you hit the lid? If you crawl around it, you're now inside the bowl, right? So this edge here represents the boundary. That's C. And so we say this thing partial S is the boundary of S, and the boundary of S is C. So what this says here is in fact true because what is partial S? It's C, which is what Stokes' theorem says.
So it's false.
No, it's true.
Oh, it's true, okay.
True. Partial S is C, which is what Stokes' theorem says. Where? Oh, yes, this is supposed to be R. Yeah. Okay. If the surface S does not enclose the volume, then the divergence theorem is useless to help evaluate the flux across S. If S is not enclosed, then we can't use the divergence theorem. False. We can, so long as we put an imaginary surface there and subtract it out later. Cool? So that one's false. Different parameterizations for the same curve C yield different results for the line integral of f ds over C. Different parameterizations yield different results. True or false? False. Different parameterizations yield the same result. Doesn't matter how you parameterize it. Parameterize however you want to, but as long as your parameterization is correct, you should always get the same answer. All right. Curl of the divergence of f always returns a vector. This kind of goes back briefly to what a curl is. Remember, curl is put these up here since you're going to need these. All right? This is the gradient dotted with the vector field. So the result is a scalar, or some function that's not a vector. But anytime you do a cross product, the cross product always returns a what? Vector. The cross product always returns a vector. The problem with this thing, though, is that though it looks tempting to say yes, because after all, the curl of anything is supposed to be a what? A vector. You have to be putting in something that makes sense. You can't take the... What is the divergence of f going to give you? A number. So can you take the curl of, say, 7? No, you can't. When you're taking the curl, you have to be taking the curl of a what? A vector or a vector field. So what does divergence of f give you? It gives you some number, like maybe like 7. And then you can't take the curl of that because it doesn't make sense. Think about this. Think back to exam 1 when I said u cross u dot v. Is this possible to do? The answer is no. What does u dot v give you? A scalar. Can you cross a vector with a scalar? No. Can't be done. You can't cross a vector with a scalar. So in the same way, you can't take the curl of the divergence of f because it's taking the, you're basically doing cross product with a vector and the number 7. Which doesn't make sense. You have to cross 2 vectors. You have to, or this has to be a vector. You have to take the curl of a vector field. All right, divergence of the curl of f is 0. It's true so long as what? The 0 that you're looking at in this problem is what? It's a vector. But the divergence produces a what?
Scalar.
A scalar. And in general, and this is something you can prove on your own, but this is always true. So put a star next to this one. This is always true. This is always true. The divergence of the curl of f is the number 0, not the vector 0, not the 0 vector. So that one's false. Those previous curl of div f equals a vector is false, and divergence of the curl of f equals 0 is also false. It needs to be a skinny 0. If the divergence of f is 0, then f is incompressible, and if the curl of f equals 0, then f is irrotational. True or false? What's up? It's absolutely false. It should be a bold 0. Curl of f equals bold 0. That's why it's false. Don't fall for that. The definitions are true so long as you're using the bold 0 and you're using the skinny 0 for the first guy, right? These are things that Kieran would do. According to the fundamental theorem of line integrals, the circulation of a conservative vector field along a curve C is 0. True or false? Nope, false. Why is it false? Circulation is just the same thing as f dot dr. Is f dot dr equal to 0 for every curve C if f is conservative? Has to be closed. Did I say C was a closed curve here in this problem? Does it say C is closed?
No.
No. It just says along a curve, doesn't it? It says along a curve C. So this is false because C has to be closed. So you could start right next to it. True. It would be true if C was closed. And lastly, if C encloses a region D, and if f equals negative 1/3 y, comma 2/3 x, then f dot dr gives the area of D. This is a tough one. Let's talk about this briefly. According to Green's theorem, what would I be computing? Instead of doing f dot dr here, instead of doing f dot dr, I could instead do the double integral of what? What does Green's theorem say? It's partial g, partial x minus partial f, partial y. What's the partial derivative of my second component with respect to x? Look at the vector field. There's a silhouette. It's just really weird. What's the partial derivative of my second component with respect to x? Please, God, someone get it? 2/3. And what does Green's theorem say from there? It says minus the partial derivative of the f component with respect to y. What's the partial derivative of the f component with respect to y? Negative 1/3. What does this give us? More, namely, the double integral of 1. What does the double integral of 1 give us? Area. So is this true or false? True. All right, I think the review's over. I can't go back to Stokes, it's not enough time, but we can look at some of these questions. Some that I think might be interesting when we look through. Let's look at number 4. So this is the second page of problems, number 4. It says let f equal g, f, little g, little h, and g equal l, little m, little n, be a differentiable vector field, and let C be a simple closed smooth curve given parametrically by R of t equals blah, 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 from t equals a to t equals b. Which of the following are true? F dot dr is the same as f dx plus g dy plus h dz. That's true. You can write, that's basically doing the dot product out for you. It's saying this is f, and this is dr. Is this f dot dr? Or rather, this is f, this is dr. F dot dr would give you what? F dx plus gdh, or gdy plus h dz. Cool? Look at number 2. F dot t is equal to negative of the integral of f dot t if you negate the direction. True or false? Why true? Is it a vector field or a scalar field? It's a vector field, so that's true. What is this thing? F plus L x prime plus G plus M y prime plus H plus N Z prime dt is F dot dr plus G dot dr. Looks good to me. Yeah? And then if f is conservative, the integral of f dot t equals 0. It's true only if I know that C is what? Is C closed? Whoa, is C closed? Look up in the original problem. Let C be a simple, closed, smooth curve. It is closed. Pay attention. So the answer is E. All of those are true. I think. Ooh, connected, simply connected. Let's talk about what that would mean. So, number 5, what time is it right now? We got 14 minutes. So this is the region in question. The question is this connected? The answer is yeah, it's connected. You can get from any point to any other point. So here, take a point here, and take a point over here. Can you get there by drawing a path? The answer is yeah. Now, it's not simply connected. At least I think. I don't know how he explains this to you, but at least when I learned in my topology class, like 3 years after Calc 3, it says that if you draw a circle inside here, can you shrink the circle to a single point without leaving the region? No. If you try and shrink it, you shrink to this. The absolute most you could shrink it is to there, right? But if you shrink it anymore, you're suddenly outside the shaded region, right? So it's not simply connected. Is that how he's described it? Yes? I don't know. All right. You don't have to use that if you don't want to. The curve x squared plus y squared equals 4 is closed and simple. So that's a circle. Is it closed? Yes. Is it simple? What does it mean for a curve to be simple? It doesn't do what? What's up? This is a simple curve. This curve is not simple. It intersects itself. Okay? So x squared plus y squared equals 4 is closed and simple. That's true. The curve x squared plus y squared equals 1 is closed but not simple. No, that's simple. Right. Okay. So the answer number 5 is it's connected, but it's not simply connected. So 1 and 3, which is answer choice D. Cool. Let's look at any other ones. Look at number 7. True or false? I'm going to be honest with you guys. I don't see anything tricky about this. I wrote this on the board at the very beginning of the review. Phi of R of B minus phi of R of A. Oh no. Why is it? Oh no. It's true. What do we need to know about F? F has to be what? Conservative. Is it conservative?
Yeah.
Why do I know F is conservative? It didn't say F was conservative.
It's
It's
the gradient.
the gradient of a scalar field, right? So because F is capital F, the vector field is the gradient of a scalar field, I know that F is conservative. Look at number 14. The standard orientation of a closed surface has normal vectors pointing out of the region bounded by the surface. By standard orientation, they mean positive orientation. True or false? True. Remember, positive orientation means it's pointing out of a closed surface. Negative means it's pointing in. Let's look at 15. Let D be a connected and simply connected bounded region in the xy plane, and the boundary of D be smooth with a counterclockwise orientation. If F equals F comma G and F and D are differentiable, which of the following are true? Basically, it's trying to set you up for Green's theorem, right? It says that F dot dr is equal to the double integral of partial g partial y, so g sub y minus f sub x dA. It looks really good. It almost looks identical to Green's theorem, but it's not. Why is it not Green's theorem? Yeah, the y and x got switched, right? It should be you take the partial of g with respect to x, and you subtract the partial of f with respect to y. These are wrong. This needs to be an x. That needs to be a y, right? Did you catch that? Good. Green's theorem says you do partial g partial x minus partial f partial y. That says partial y partial, or partial g partial y minus partial f partial x. That's wrong. It's just one small thing that Kieran's going to try and do. He's going to switch that x and that y. You're not going to notice a thing. But that's not Green's theorem. Green's theorem is partial g partial x minus partial f partial y. If partial g partial y minus partial f partial x equals 1, then the area of D is given by the line integral. Again, that would be true if what? If it was partial g partial x minus partial f partial y. If f is conservative, the area of D is 0. Ooh. Yeah, it is. Why? If f is conservative, and the curve we're integrating over is closed, what's f dot dr automatically? Wait, no. What? 3 is false. 3 is dumb.
Why is it false?
Why is it false?
Yeah.
Because, okay, what's the area of that region? Let's just give me a number.
Not 0.
Not 0. 97 pi. Sure. Looks like about 97 pi square feet, right? Yeah. Okay, so what's the integral of f dot dr? Well, let's say f is conservative, and this is a closed curve, right? So what's this integral going to give you if f is conservative and the curve is closed? If f is conservative and c is closed, this gives you what? Automatically 0. What was the area? 97 pi. All right, I don't think I have much time left, so I do want to do one last thing. Sorry I didn't get to go over everything. I wish I did. Is there one other thing I want to look at? Not really. You can ask me questions on the wall on the Facebook page, of course. One last thing I want to point out, though, is the very back of this page or paper is blank, and on it I want you to draw the same thing that we drew that we get at the end of last session. F dot dr. Is f conservative? The answer is yes. Draw a branch for that. The answer is no. Draw a branch for that. The next question you ask yourself is C closed? If the answer is yes, then f dot dr is 0. 0 is your answer. If it's not closed, then you just use the fundamental theorem of line integrals. You do phi of terminal, phi of b, let's say phi of r of b, minus phi of r of a. Terminal minus initial, phi of terminal minus phi of initial. If f is not conservative, we still ask ourselves, is C closed? If the answer is yes, actually let's start with what happens if the answer is no. If f is not conservative and C is not closed, you have to do the usual 4 steps. We'll say 4 steps. What are those 4 steps? Step 1, do what? Parameterize. Step 2, do what? Compute the RU cross RV or the R prime or whatever, the magnitude, R prime T magnitude. Plug in, and then step 4, integrate. If C is closed but F is not conservative, what can you use? Green's theorem. That's an F. Whatever. Green's theorem. You use Green's theorem. Cool? That's G's T. Green's theorem. Cool? All right. We got 7 minutes. I'm taking questions now. Hope you enjoy the video.